I'm Laura, and today I am going to discuss thermochromic glass. First, we should define thermochromism. This is a reversible transformation accompanied by a change in color, which is caused by heating and cooling. These are some of the categories of thermochromic materials, starting off with liquid crystals. As they get heated, their structure goes through different changes. But the structure that we care about is the nematic phase, which is the one with thermochromic properties. Light passes through the crystal and then diffracts off of the layers, and only certain wavelengths get reflected, which corresponds to the color that we see. Changes in temperature change the spacing between the layers and therefore the reflected color. So the color that we see can range from any color in the visible spectrum. Leucodyes are a type of dye that can switch between two slightly different structures, one which is colorless, the leuco structure, and one that is colored. However, to get a specific color, you need to choose the correct corresponding molecule, and the temperature that activates this change is not as precise as with liquid crystals. Lastly, we have inorganic compounds. A lot of these compounds exhibit subtle color changes upon heating, such as zinc oxide, which is white at room temperature and changes to yellow when it's heated. Vanadium dioxide is a semiconductor at room temperature, allowing infrared to be transmitted. But above 68 degrees Celsius, it acts as a conductor and reflects infrared, which I will go into more detail later. This is also accompanied by a change in color. Here are some examples of the different materials being used for thermochromic products. Again, liquid crystals can range through the whole spectrum of visible colors, and the response colors are very specific to temperature. So one popular use that a lot of us have seen are in liquid crystal displays, which are common in TVs, computer monitors, phones, and similar products. For leucodyes, since the response temperature isn't as specific, it's used a lot for novelty or gimmicky products, like spoons that change color when they get cold, commonly used in ice cream shops, or coffee mugs that reveal a hidden design when hot coffee is poured into the mug, and so on. Lastly, here's an example of thermochromic glass, with the glass pane on the right being the hotter one in the reflective state. So moving on to vanadium dioxide, at or below 68 degrees Celsius, which I will refer to as the transition temperature, vanadium dioxide has a monoclinic structure. In this phase, the vanadium-vanadium bonds alternate between short and long. Above the transition temperature, the structure is tetragonal rutile, and the vanadium-vanadium bonds are all the same length. So in this unit cell for the tetragonal structure, which again is above the transition temperature, the vanadium ions are in body center and corner positions, with each atom surrounded by 6 oxygen atoms. So the blue ones here are vanadium and the red are oxygen. The vanadium ions are aligned in linear chains, with the vanadium-vanadium bond distance being constant in the vertical axis. So this is just one unit cell. If you imagine another one of these stacked on top of this one, the distance between the vanadium atoms in the vertical axis would be the same. Because of this, all the vanadium atoms have equal sharing of d orbital electrons, which results in the metallic behavior that we see. However, in the monoclinic structure, which is below the transition temperature, dimerization causes vanadium atom chains with alternating short and long vanadium-vanadium bonds. This pattern localizes d orbital electrons within the dimer, which results in the insulating behavior. So as you can see in this unit cell, on the right side, the first 2 vanadium atoms have a longer bond distance than the 2 on top. And then on the left side, you can see that the first 2 vanadium atoms have a short bond distance, and the ones on top have a longer distance. So now we know that vanadium dioxide can transition from a semiconductor, which allows transmittance of infrared light, to a metal which reflects infrared light, and that this transition happens at a certain temperature. But this isn't useful yet because the transition temperature is 68 degrees Celsius, and it would be practical for this temperature to be lower if we're going to use it in glass for windows. This is achieved by doping the vanadium dioxide with tungsten. In the study by Tan, Yao, Long et al., they used X-ray spectroscopy to analyze the structure of vanadium dioxide that was doped with tungsten and found that the local structure around the tungsten atom is intrinsically symmetric. This symmetry essentially forces the asymmetric monoclinic structure to form the symmetric rutile structure. So more tungsten makes this transition easier, lowering the transition temperature. As you can see with the plot on the left from that study, there's an approximately linear relationship between the increase of tungsten concentration and the decrease of the transition temperature, with a decrease of about 30 degrees Celsius per atomic percent of tungsten. A similar study was performed by Shen, Dong, Cao et al. They used differential scanning calorimetry, which measures how much heat flows into or out of a sample, to determine the transition temperature. So the transition temperature for each corresponding sample is where it forms a peak. They similarly found that the transition temperatures linearly decreased by about 28 degrees Celsius per atomic percent of tungsten. So why do we care about vanadium dioxide and lowering its transition temperature? We care because it can be applied to glass as a film, and since it would reflect infrared, this would reduce heating and cooling usage, thus reducing energy usage. Glass with a vanadium dioxide film is still being researched, but currently on the market is glass with a low E coating, which achieves a similar effect in terms of temperature control. It's called low E glass because it has a thin coat of material with low emissivity of infrared light. Depending on the manufacturer, this material could be silver or indium tin oxide, for example. However, this glass does not change color, so it is not thermochromic.